Ah, yeah? Yeah. But the tram in that's something like that in that's normally to happen. Yeah. Hi. Oh, this is so nice. Yeah. I'm already. It's okay.
Okay, so yeah, very happy to introduce our visitor here is giving a talk, Yutaka Shikano,
Yeah.
so professor at the University of Tsukuba in Japan,
Yeah.
also affiliated with Chapman Institute in the US. and we'll talk about the observer-dependent description of quantum states for indistinguishable particles. So,
Yeah.
thank you.
Thank you so much. Yes, thank you so much for the kind introduction. And also thank you so much for the kind of hosting me to come back to here. That's, how to switch to that presentation? Okay, thank you. I'm from the University of Tsukuba, and today the manual explained to me, explained to us, observer-dependent description of the quantum particle in that identical particle is. And before that, I'm working on this. I'm introduced by myself. I graduated in Japan. That's the Tokyo Institute of Technology. Unfortunately, right now, that's the university name was changed. It's right now that's the Institute of Science Tokyo. Right now, that's my institute. That's here, and also during the PhD, I visited to the MIT. Since after that, I graduated the Tokyo Institute of Technology. Then thereafter that, I Institute for Molecular Science. I was 5 years spent on the PI, and also the University of Tokyo, and the Keio University, Gunma University, and moved to 3 university. Right now, I moved to since last October, no, 2 years before October, I moved to University of Tsukuba. This is my history of my research history is the first one in quantum mechanics on mathematical physics side, and also the quantum work in the quantum weak measurement, such kind of like this. And also during the Institute for Molecular Science, I working on the photophysics stuff and that gravitation wave detection, since coupling to the precision measurement science. Then thereafter since the University of Tokyo, I moved to the quantum computing project. I should join, and also the quantum random number generator, such kind so on, and also that's similar kind of the manner. This is since so many variety of the field I working on there. My heart rely on the quantum foundation stuff. That's why today I'm talking about it. I choose this today's seminar. And also, right now in the University of Tsukuba, maybe as you maybe know, as you maybe not know, that's the way the Tsukuba is. And as you maybe know, that's the capital city of the Tokyo. Tokyo is the biggest city in Japan. And that's the center of the downtown. We have the 2 big airports, Haneda and Narita. Is both of the side in my University of Tsukuba, 60 kilometers far away. That means roughly that's a 1 hour train or 1 hour bus, roughly speaking. Then when you come to Japan, please visit to Tsukuba. Yeah. Then today I'm talking about in the history of this quantum mechanics. First of all, in 100 years ago, of course, as you maybe know, this year is 1925 when Heisenberg founded the mathematical foundation of the quantum mechanics. Is this time in I'm rely on this. That's Shinichiro Tomonaga, one of the Nobel laureate, is a Japanese Nobel laureate, wrote it the essay of the trial photon. This is the essay mimic to that trial in the reacting on that trial photon right now. This with the musical director, collaborate with the musical director. I'm conducting on this project right now. Then since that's after 1925, how did you physicists convince the formulation of the quantum mechanics? That's the problem. In 1 year after, Paul Dirac and Werner Heisenberg, both of us, they attacked to the helium atom problem. Helium atom, in very, very easy to problem, is 2 proton, 2 neutron, and 2 electron. This is the 6th component of the system. At that time, in the electron has 2 identical particles. That's why X1, X2, this is coming from Paul Dirac's paper. X1, X2 can be exchangeable. This is due to this effect, they are succeeding on to explain the electrical structure of the helium atom. This is a very important point of this today. Why is that the two electron has the identical? This is that's the today's problem is. And also that's the since after so many people that's the mention about this is that the identical particle was assumed. For example, in the thinking about the water itself, that's water, in that that's water is not identical maybe. This is a distinguishable. But inside the water, we compound water molecule. Water molecule itself, we have to exchange them. This is the identical particle can be taken as. And also, inside this water molecule, this is a we compound this atom. Atom itself is the electron inside the atom is a we compound the electron that's the nuclei. Electron itself can be taken as some fermion, such kind of so on. Then that's we have to taking out identical particle behavior. Then after that we can succeed on to calculate it electron structure normally. And also nuclei in the proton and neutron, in the quark, everything can be taken as the identical particle normally, even if that's same particle. And also we can classify the boson, hadron, fermion, such kind of so on. This is normally we taking as we deal with this kind of the standard quantum textbook behavior. Then that's the move to change the topic. One thinking about the photon, single photon, we have to thinking about the quantum eraser problem. What is the quantum eraser problem? Is one light in that one point beam coming from to the double slit. Then thereafter that we have to go to the slit. D0 in the screen. In the standard cases, that's it. But after the slit, this is the BBO crystal. This is a spontaneous down conversion. We created two photons. Such kind of cases, another photon coming to that downside. Downside, even if that D4 is a click, that means in that the photon coming from that the upper side of the slit. D3 is a click, that means on that the downside of the particle photon transmitted to. And the D2 and the D1 putting on the beam splitter, we have to interfere. We cannot distinguish which slit photon is passing through. That's why D1 and D2 is a click. We cannot know which particle coming from, which slit the photon can be transmitted to. Then that's something like that. In that experimentally demonstrate that D1 and D2 is the cases in that interference pattern we will see. D3 and D4 cases, single particle slit that can be taken as. That means photon seemingly knows that which particle, which slit can be behaved. That means seemingly on that the breaking on the identical particle picture or not. This is one example. Then this is today's I have very pedagogical quantum mechanics. I want to extend it to two-particle quantum mechanics. Two-particle quantum mechanics, normally in the textbook, the wave function amplitude transmitted to the A to C, B to D. That's the sum of it's an initial state A, B. Such kind of cases, in this transition amplitude, and also A to D to and it's a B to C, that transition amplitude is exactly same. This is why amplitude depends on the indistinguishability. Even if that's the A and B is an identical particle, that transition amplitude is exactly same. That's the example. There's two photon interference pattern cases. Fully distinguishable particle cases. That particle is one photon coming in, one photon coming into the beam splitter. go to that's the four possibility. 2 photons coming into the left-hand side, 2 photons simultaneously right-hand side, or 1 particle goes to the straight transmitted, and also both ones is reflected. That's the case. Fully distinguishable particle cases, nothing to happen. Changing on that the delay of that arrival time differences, we did not see that the number of the coincidence, that's the same. But indistinguishable particle cases, we cannot distinguish this side and this side. Then that's the phase difference is exactly same. That's why we can interfere on that side. Transmission, industrial reflection, exactly same. That's why industrial interference, that side is nothing. This is a Horn-on Mandel dip effect in that, as you maybe know. This is that we can see there, such kind of stuff. From this point, photon recognizes seemingly that distinguishability. This is because photon did not know that's each of other. This is before coming to the beam splitter. That's identical. This particle did not know that particle. But the same to that beam, simultaneously coming to that beam splitter, meeting there, then interfere or non-interference pattern we will see. That's why in that photon seem to be that's in this photon recognizes distinguishability. That's why today it's another 2 kind of system. I can show you this example. Yet I did not know that honestly before coming. This week there's Anton Zeilinger's birthday in that week, and also that symposium was held, and also that we are so happy that he demonstrated that the EP very inequality violation. That's very surprising for us, and also since that's the beginning on going back to the EPR paradox. Yeah, we can source to that A to B. Then normally we can taking as description of that entanglement state up down to that down up, for example. We share the Aharonov-Bohm for the maximum entanglement state. We measure that Alice spin. Such kind of cases, Alice can evaluate the Bob spin state. Such kind of cases depends on the Alice measurement outcome, and that's the spin up or spin down. This is the normal thing. But Bob did not know Alice was happened. At that time, Bob estimated on his own state. He can evaluate it as a complete mixed states picture, normally. That's why, from this point, quantum state description does not only depend on the particle, but also that's a measurement objective information. That's why it is really important is that observer should be know or this state is this identical or not, or this is that the state itself in that now is a measure or not. Depend on it, depend on the measurement outcome, or just that's what we did. That the quantum state description should be changed. This is actually a quantum information standard behavior, standard textbook demonstrated that this interpreted this is a quantum state. What's happening is. Then today's question is there this setup information dependent indistinguishability is also the same thing or not? This is today's question. From now on, I would like to propose to that the 2 particle cases to the extended 3 particle. Very, very simple. 3 particle, 1, 2, 3. And also the 6th side. And also that's another 3 particle is the white one. 3 identical particles with 2 configuration cases. From now on, we consider. This is the demonstration experimentally. This is the From now on, that's why I explained how to experiment demonstrate it. 14 calcium ion cases, sorry. Calcium ion, this is due to the Coulomb interaction. We formulated the triangle. And also, another triangle is the white one. We transition, this state transition, clockwise transition or anti-clockwise transition. That's the situation we demonstrated that this kind of state. From this experimentally demonstrate, how to demonstrate it, this experimentally, we created the ion pole trap to the trapping of the 3 ion. Segmented pole trap cases, we can trap to the 3 particle. And also, we shining on the laser, 300 almost 400 nanometer laser, shining on that's a different state. Thereafter, the fluorescence from the ion, we can measure of that image from the ion. Then that's how to formulate it on the position, conformation, this up triangle or down triangle. It is easy to distinguish those two. Then that's how to trapping on the ion trap. And that's the sum of the kinetic energy plus the Coulomb interaction. This is as I said. And also collective motion of that's the moving down to the ion itself. This is moving around, there's any motion. But 3 of the collective particles of the ion can be taken as the Coulomb crystal, normally, we call. They can be taken down to the motional ground state. Normally, this is the ion trap quantum technology of that ion trap. Normally, the collective motion of the ion can be cooling down motional ground state. Then, from even if that's we demonstrated, that's the motional ground state, we trap to that down up triangle to transit to the down triangle, clockwise transition cases, anti-clockwise cases. Two directionality, we cannot distinguish. We cannot distinguish clockwise and anti-clockwise. This is because 3 ion exactly same. Energy, spin state, anything. That's why we did not see which rotation will happen. That's why in the seemingly, this is a double slit experiment that can be taken us. Why? And that's also the similar potential of the case of this ion trap plus RF trap potential. Such kind of cases, normally this is the distance is 7 micrometer, roughly speaking, of that 2 ion. Roughly speaking, 7 micrometer equal triangle we created. And also radius cases, that's something like that. 6 local minima. We putting on the ion, it's due to the Coulomb interaction. We formulated that triangle or that triangle. Then that's what we created there. And also, that's a linear pole trap cases. Normally, linear pole trap case, RF potential, normally that's something rotational electric field. Even if that's a straight line cases can be cooling down due to the sideband cooling of the technique. But unfortunately, 2-dimensional motion of the conformation of the ion, as that case, RF field, oscillation field, hitting on that gradient of that electric field of that charge particle. That means in that Lorentzian force, we inserted on the charge particle in any case. But normally, experimentally speaking, normally we cannot cooling down any kind of the motion of the collective motion of into the ground state. But we found particular collective motion we can cooling down into the ground state. Then that's from now on, we decompose that's the 3 decomposition. There's a n position, n ion, and that has a 3n collective motion normally. This is because the 3D is that the collective three-dimensional mode. That's the coupling to the three-dimensional mode. Then that's why 3n collective mode. That's the 1D case. That's we are now in the 3. That means that's the 9 collective motion. For a 6, in that the 1D cases, ion cases move to the everything the light, everything that's some oscillation, for example, or middle is that's here, and that's the right-hand side here, that side here. That's any kind of the decomposition we can consider. And also two-dimensional cases. Two-dimensionality is that's the case. Everything light, or that's the same thing like this. This is the 1, 2, 3 times the 12 collective motion. But the degeneracy of this motion, this is because that's this collective motion, this is the rotational mode, can be decomposed linear combination, that's motion plus that's motion. That's why this 9 collective motion can be reduced. Then it's a normal frequency, normal frequency of this changing the trap ion potential, changing the trap ion potential, such kind of cases, rotational mode can be cooling down to that ground state. That means the normal frequency of the mode of that is exactly 0. This mode in that blue point in that some zigzag motion. Zigzag motion is also that similar kind of manner. This is the sum of the point, only that point, 1.75 megahertz. This is the technical thing. It's a 40 calcium ion cases. This can be cooling down into the ground state. That means also the zigzag motion is the freezing. That means that it can be taking the straight line. Rotation mode in that can be go to the ground state, mean is that like that the many kind of the motion of that like that the merry-go-round. Merry-go-round type of this trap potential we created. Then we take to the picture of the 4 point on the 1, 2, 3, 4. We fix. Thereafter that we take the photo of this ion. Such kind of cases, as I said, it does the zigzag motion freezing. This is the simultaneous at this time, one-dimensional degree of ion can be formed. Number 3 is a slightly triangle. Number 2 is a triangle normally. Number 1, this is, as I said, one bottleneck potential, VBC. Then this is the ion moving quickly too fast. That's why we did not see it, that the ion is where it is, into the ground state. Then we choose near to 1's position. That's the frequency, and also number 2 position. This is using 2 point we created to such kind of cases. That's what I want to explain to the experimental procedure. First one, we created the triangle state. We confirmed that's the up triangle. Thereafter, that's the sideband cooling is the waiting for the time into that shifting to the trap potential. Thereafter, that we measure to the second time, or up or down. This is a simple experimental procedure. Transition probability is from that one side of the triangle, up triangle to the down. How much transition to the up to the down. That's only this. First of all, we experimentally demonstrated sideband cooling. We catching there. Due to that quantum technology, the Doppler cooling and sideband cooling technology. Before sideband cooling, we are normally mean phonon number, industrial number is 10. But after the sideband cooling, one particular motion, this is almost greater less than 1. That means into the ground state normally. Then, what's happened? Sorry. And also we calculated on the sort of top potential near to that wine bottleneck potential position. Such kind of cases, wave function can be calculated, should be overlap. And also, we have to that into the ground state, roughly speaking, right now, that's 150 hertz. This is now we estimated there. At this time, down triangle, up triangle of the case, this the wave function should be overlap. That means tunneling is we have the chance to the transition. Even the clockwise transition, anti-clockwise transition, we have to see there. That's a quantum tunneling. That's why in that we created that up triangle. We shifted to that clockwise motion, anti-clockwise motion, micrometer scale. This is a quantum tunneling occur. Then that's we checking the first of all without magnetic field. We demonstrated that the transition probability. We changing the time, weighting of the time of the tau. Normally, we have to that's the oscillatory behavior and also that's the exponential curve. Exponential curve, why? It does as I said, two-dimensional cases. RF trap potential, we heating up. Then that's the triangle motion. This is the classical motion we created. That's why in that's the heating effect, how much heating effect plus coherent tunneling part, we can fit it. At this time, and that's the T2 is that's the roughly 500 milliseconds. 300 milliseconds, sorry. And also trap potential, that's the 7 hertz. That means roughly 50 milliseconds, one transition we occur normally. That's the transition, that's the up to down. That's transition, that's the roughly time scale, that's a 50 milliseconds. In the average time is the tunneling occur. Then we confirm 3 triangle and also, that's the 3 ion. We created 2 configuration of the triangle. That triangle transition, 50 milliseconds. And also the clockwise or anti-clockwise. Then from now on, this is we inserting of the magnetic field in the center. Such kind of cases, now is the 3 indistinguishable charge particle, changing the charge particle coupling to the gauge field. There's an Aharonov-Bohm effect we observe. Then that's we calculated magnetic flux. Theta is that's now in that's the half of over 6. That's the 6 configuration. That means that's the total one circle in the magnetic quanta. We can calculate it. From now in the 2 pi single magnetic quanta. This is the standard cases of AB phase. And also the times the 3, where this factor is where it's coming from, 3 indistinguishable particle. That's the effect. That's the quantum phase we observe. And also transition probability is so easy with the AB effect. This transition and this transition, this is the phase in the opposite. Then that's it is easy to interfere. This is the C exponential I theta over 6 or plus exponential minus I theta 6. Then cosine, that's the cosine term, that's we remain. This is easy to calculate like that. 1 plus beta. Then we perform, then we fix to that's the tunneling time, that's 50 milliseconds. As I said, there's a 1 transition occur, and that's changes to the magnetic field. This is we demonstrate that's experimentally. This is changing the magnetic flux. We observe the transition probability. That's the oscillatory curve we observe. This is almost 10 years ago. This is we demonstrated there. Sorry, that's this kind of thing. Yeah. Now, this is a we succeeding on this kind of setup, and also the AB effect, we, even in the quantum tunneling gauge coupling, this we observe. Unfortunately, that's we, theoretically speaking, we did not know why is that the quantum, even the quantum tunneling gauge coupling that's still occur. I don't know why, but experimentally showing, demonstrated that's the result. And also, now the two configuration, that's the identical particle cases. Changing the one spin is a flip. For example, that's an ion, isotope control, changing to that's a 40 calcium ion to change it to the 41 calcium ion, or spin state that change. That means the spin state inside it, this ion trap cases, electrical state slightly change. Such kind of cases, we can label to that some kind of cases. On that, we initially prepare that triangle is a similar manner. Thereafter, that this kind of the transition in the three possibility, clockwise transition, that's probability j times exponential theta over 6. This is no interfere. Anti-clockwise cases is also. This is nothing to happen. This is a remaining of the probability. This is so easy to calculate it. But this is a no interference pattern. This is everything we know, only the one spin flip. Only the one spin flip. Previously, two configuration cases, interference pattern we observe. That's this configuration, only change the one spin flip, no interference pattern. That's configuration. But that's a which configuration, those configuration, this is an interfere or not. That's why that's I question to do. Which point of the particle can be recognized as popping? That's popping to the here. Go to that the downside cases. Red particle move to the right hand side, left hand side. Such kind of cases, we have the chance to interfere. But it's an experimental demonstrated. It's so might be possible, but not so easy. Right now, that's our question is today, information dependent setting. We shade similar manner of the EPR. Half of the part we shade of this. How to shading on it experimentally? We shining on the laser, as I said, in the 400 nanometer laser pulse. That's in the beginning. On that's the CCD camera we detect. Now this triangle 7 micrometers far away. Then that's the beam size in that's the very constrained. That's very narrow. We shining on this downside only. This is it's not so easy, but is feasible to demonstrate it experimentally. In that the only two we confirm 3 possibilities, this configuration, first of all. Thereafter, the final point, we did not observe in that upper part. At this time, what's happening? Of course, that's the transition. This is occur. In this situation, we have to consider 2 possibilities. First one, possibility 1, in that when a particle goes to here, still the 2 particles remain. When the particles themselves recognize the distinguishability, like the quantum eraser problem, such kind of case, this setting should be labeled to the particle. This is because the particle already know which particle 1, 2, 3, or 1, 2, 3, or 1, 2, 3. Yeah, that's the label. Such kind of cases, yeah, okay. This is a transition. Yeah, sorry. if that's this label to the 1, 2 cases, 3, that cases, this one particle hopping to this side, if that's the case, even if we open to that shade region, and that the 2 particle is the second particle label is moved to the right here, and also the red point in that anti-clockwise transition we observe. But we did not know, but particle knows that the Fitch rotation happened in this situation. This is very important. But in this setup, as I said, particle should be labeled. There's no interference pattern. Even if that's the assumption is, as I said, again, particle should be labeled when that's the particle recognizes indistinguishability. Question number 2. Situation is different. Observer did not know Fitch rotation happened. This is because this kind of setting of that shade of the upper part, this, even if that's the left and right in that particle here, but this transition, clockwise, anti-clockwise, we did not know. That means, we did not know means, this is because that's the upper part, upper area, red particle clockwise or anti-clockwise. We did not know. Such kind of cases, we did not see there. That's the observer did not know that's a Fitch particle position. Like the APR paradox situation, similarly. That means there's a coherence seems to be kept. That means there's an interfere between those two. That means that the transition is that here, and also the clockwise and the anti-clockwise transition. This transition probability we calculated interference pattern we observe, we expect to do. These are exactly same setup, but situation, the theoretical assumption is different. Theoretical assumption is that the first cases, particle recognizes indistinguishability. Second cases, this is like that's the quantum information textbooks, measurement of that's the quantum state. Similarly, on the part, observer did, in front of the observer, what situation happened? Which one is that? Which one situation will happen? We summarizing, we can verify experimentally which assumption is right. That's why in this I propose that this setup in that the particle knows to that indistinguishability or observer decided the distinguishability. Which one is that preferable? Then that's it. That's my proposal. This is we propose to clarify situation that whether the distinguishability of the particles is known by the particle themselves or observer. Which assumption is right in that we can testable in this, and also this setup experiment, setup realization using that ion trap experiment with the AB effect, and also that's we have to. Sorry, that's I wanna writing the paper before coming to the seminar, but unfortunately I have no time. I now is preparing of this paper, and also I have to extend it much more. For example, how to affect the many-body system. Many-body state is also that the similar manner. There's a fermion boson, similar parastatistics, so many things. This is that similar kind of the question will happen. And also how to understand there's a time crystal. This is that situation. Time crystal means spontaneous symmetry breaking the time. This is the same setup of exactly same setup ion trap. In that clockwise motion, anti-clockwise motion. This is a unidirectional motion, even if that's the symmetry breaking of the time. Unidirectional motion we observe. Then that's the similar manner of the time crystal we can understand that that's this setup. Then that's I wanna know that's a similar kind of the setup to do. That's it. Thank you so much for your attention, for your listening. Yeah. Oh, here it is. Vienna style as well. Yeah. Thank you.
Okay, thanks a lot. Are there any questions from the audience?
Yeah.
Isn't distinguishability requiring interaction with observer by default? Maybe I'm misunderstanding something, but
yeah, that's the good one. Yeah, normally quantum state before that the measurement observer independent of the situation. Quantum state itself, we have not yet described. That's the situation defined by that observer. Then that's we can create it. We can describe the quantum state. Similar manner of the observer decided, oh, which region, whole region we measure, or that's the downside region we measure. We have the possibility, of course. In advance, even if that's we measure that's the observer side, that the observer decided to the downside of the region, that means the similar manner of the shade of the upper side. Such kind of situation, if identical indistinguishability decided on situation dependent means observer decide a measure in the downside or only, or whole situation we measure. Distinguishability situation should be changed. That's the observer dependent situation.
yes.
That's at that time, this situation, this experimental setup, we demonstrated, even if that's demonstrated on that situation, AB effect we observe. That means not an interference pattern we can observe. But particle itself, normally this is the identical particle behavior. In the standard quantum textbook, electron ion that's the same. Identical particle is a particle behavior. Particle intrinsic behavior, that means particle should be already known which transition will be happen. Such kind of cases, such kind of scenario is right. Such kind of cases, no interference.
What does it mean that particle knows? This is
Particle knows. Oh, okay. Particle knows means is that
that it's determined already what is going.
Yeah, that's situation. Yeah, experimentally that's we created. Yeah, that's my question. That's very simple. Water molecule, we have to inside there. That's the several electron we can that's the consist of this the water molecule. That's electron, identical particle. But same energy, same distance, anything like that. That's water molecule here. Another water molecule here, for example. This electron, that's electron. We did not say that's the identical particle. Normally. This is far away from here. That's why. This is the same setup. And also the Coulomb interaction, anything like that, that's the same. Only this is a change far away from that one particle, another particle here. This is the identical particle. It should be, or it's a possibility to describe this identical particle. But Only that's the one particle side inside it, we can take in as the identical particle. Particle knows mean on that's the intrinsic behavior of that's the indistinguishability or not. Or this is a much more experimental question. Inside that's the molecule, or that's the one inside the atom, this position slightly changes the magnetic field. Slightly, very, very slightly. Exactly same cases, this is the exact energy. But slightly changing, very slightly, that's the changing the magnetic field, Zeeman shift of the effect, that's different. That means the quantum state slightly different. That means in these cases, distinguishable particle, why is we can deal with, in principle, one Atto-Gauss, for example, one Atto-Gauss differences in that one, this side and this side of that's the magnetic field, but the same description of that's the same description of the identical particle, normally. And also that we can deal with that identical particle description. We can succeed on that's electron structure, for example, helium atom or something like that. We are so many beauty. We have so many sort of insightful, useful insight from that identical particle description intrinsically. But is this true or not? That's my question. Yeah.
Okay, thank you.
Yeah.
Are there any other questions? So.
No, it's okay.
So perhaps
Yeah.
I have this one thing I was wondering about also. When you talk about this shielding, right?
Yeah.
Shielding the first one. So what I understand is that you're preventing the observer from having the information, right?
Yeah.
With this, which transition happened. This is the function of this shield.
Right.
So, but do you also need to make sure, in my understanding, that the this lower particle itself wouldn't have information about what happened upstairs,
what
right?
happened to that pulse? Yeah.
So it's not only shielding of the observer's information, but also the third particle information, or is that, because how can I make sure that this particle is not affected, just this particle from the others, even if I shield the observer's information?
Yeah.
Maybe you can talk more about this shield.
Oh, right.
Bit,
Okay,
yeah.
thank you. This is that's for example, that's for example, this kind of cases, isotope control cases we consider, for example. Isotope, one neutron added on. That means slightly changes the mass. That's the ion trap in the sort of kinetic term plus RF potential, plus that's the Coulomb interaction. Coulomb interaction is the same. This is because that a neutron is only one neutron added on. But mass is a slightly change. This is now in that's the identical particle cases, perfect triangle we created. But one neutron added on, slightly change the particle structure, slightly bent it to that perfect, slightly changing the perfect triangle. But the same question to that Atto-Gauss cases, the differences for the Zeeman shift problem. This is because that's we added on the one neutron, very, very slightly different. That's as I said, you are right. This is a transition we slightly affected to do, slightly bending to the position. And the local minima point is also the slightly change. But from our side, we cannot distinguish. That's even in that one neutron, only that's very, very small. Approximately, this is almost same. That's why it's not, of course, that's the quantum mechanical level. This difference happen, but we did not observe this difference is. That's why in this situation, measurement of observer dependence of the distribution of the quantum state, anything like that. Why is that we can treat it on the quantum information side? Similar kinds of differences, almost negligible. Almost negligible means almost same. Almost same is also that exactly same to that quantum state description. In that case. That's why my question is arise to that which intrinsic means our side recognizes these slightly differences, or our side is negligible of this effect. Which one is that feasible? But from the viewpoint of the spectroscopy viewpoint, this one side is the differences. It's not that can be distinguishable, can be clarified in the isotope differences. That's why we are changing on the experimental strategy. That particle is the same or not, we can testable from measurement observer side. But particle itself, from the viewpoint of the particle side, I don't know. Nobody knows that this particle is changing on the isotope or not. Only this is the Coulomb interaction, such kind of so on. That's it. Yeah. That's why which one is correct or not. Yes, my question is right. Yeah.
Thank you. Okay. Otherwise, if there are any other questions, and if not, then let's thank the speaker again.
Yeah, thank you.
Thank you. Yeah, I guess you'll be around for lunch and maybe afterwards.
Yeah, okay, thank you so much. Yeah, good.